Hello, everyone. Once again, thank you so much for your time. Today, I'd like to continue on our discussion on filter design. Okay, our topic for today's discussion is still on the terminologies and also the parameters that we use to describe filter design. There are three terminologies or parameters that we're going to discuss today. Number one, okay, center frequency. Number two, stop band cutoff frequency. And last but not least, selectivity factor, or we call it a quality factor. This will be the part 2 series discussion. The earlier on series discussion, I have put the video link under the description. So please go through the video if you're keen to know more about filter design. This is my email. If you have any question regards on today's discussion, please drop me an email. Before I continue, I'd like to urge you guys to support this channel by smashing the like and subscribe button. Please also turn on your notification bell in order to receive more info from this channel. Thank you so much. Let's jump straight to our first discussion, which is the center frequency, which we also denote as F0. Okay, bandpass filter are geometrically symmetric. Okay, I put it normally because normally for bandpass filter, they are actually geometric symmetric, which means that imagine this is the imagine line. Okay, you can see that they actually is a reflection from the mirror. So they look exactly the same. They look like a twin. Okay, but nowadays, for some case here, bandpass filter need not really symmetric. Okay, we also have a symmetric bandpass filter design. Okay, so hence, in order to further discuss what is center frequency, okay, we assume that this bandpass filter, they are actually symmetric. The center frequency of a filter always refer to the geometric center. Okay, so this is what it means. Right in between here, this is the point that we call a geometric center. How we can compute the center frequency? Okay, is actually a square root of F1 and F2. F1 and F2 is actually known as lower cutoff frequency and upper cutoff frequency. How can we arrive at these 2 points? Okay, for example, this is the frequency response of a bandpass filter. The highest point here, okay, minus away 3 dB. Okay, so this will be the lower cutoff frequency. Same wise on the other side, this is the highest point, 3 dB down. Okay, and then hence this is the higher cutoff frequency. Hence, I'm able to determine the F1 and F2, and hence with F1 and F2, I can easily compute the center frequency as shown in this equation here. Next, okay, let's discuss what is stop band cutoff frequency, okay, which also denote as Fs. Okay, this is the frequency at which we guarantee a minimum required attenuation. Okay, so take a look on this bandpass filter frequency response. Okay, for example, for this case here, for example, we want to have a 50 dB attenuation. So for example, over here, this is a 50 dB, and hence, these are the two lower cutoff frequency and upper cutoff frequency in order to specify that the minimum required attenuation of 50 is actually achieved after these two cutoff frequency. Hence, this is how we determine the stop band cutoff frequency for bandpass filter. Let me quickly conclude. For example, we want to have an attenuation of 50 dB. Okay, so this is 50 dB, and we quantify the lower cutoff frequency and the upper cutoff frequency. So anything before the lower cutoff frequency or anything after the upper cutoff frequency, this is where we can guarantee at least 50 dB of attenuation. Hence, this stop band cutoff frequency is to guarantee the minimum required attenuation so as they will not create an interference to your neighboring. So this is the definition of stop band cutoff frequency. Same wise, stop band cutoff frequency can also apply to low pass filter and also high pass filter. So over here, again, let's assume that this is 50 dB. So at this particular 50 dB point, and then at this cutoff frequency, anything larger than this cutoff frequency, we can actually guarantee a minimum required attenuation of 50 dB. Hence, this is where we can mark this as stop band cutoff frequency. Same wise for this high pass filter. Okay, for example, this is 50 dB. We actually mark the cutoff frequency. Hence, anything before this cutoff frequency, we can actually guarantee a minimum required attenuation of 50 dB. So this is stop band cutoff frequency Fs. Next, let's understand what is selectivity factor Q, okay, which is also sometimes called as quality factor, okay, of bandpass filter. The quality factor of the resonator, okay, is used to describe the selectivity of the filter, okay, which means that whether is it highly selectivity or loosely selectivity, okay, is actually governed by this quality factor. Okay, so later on, I'm going to illustrate with a diagram to let you understand the Q value. Okay, they basically can be categorized as the frequency of resonator divided by the bandwidth of the resonator. Okay, we will come to this shortly. So this is how we can calculate the selectivity factor Q, okay, which is the center frequency over the bandwidth. Okay, so remember for bandwidth, we always use the highest frequency minus the lower frequency. And from here, we can calculate the Q. Let's quickly do two examples in order to understand the quality factor Q. Okay, so this is the case number one. Okay, we have the lower cutoff frequency, and we have this upper cutoff frequency, and we also have the center frequency. Okay, so from here, okay, we can compute that the Q, okay, which is this formula here, F naught over F2 minus 1. So this is 4.1 as F naught. Okay, so the bandwidth is actually using 5.1 gigahertz minus 3.1 gigahertz, which is shown over here. So I can compute that the Q is 2.05. Next, for case 2 here, again the same thing here. Okay, I can compute that this case 2 is actually equals to 0.91. So from here, okay, I can conclude that this is higher Q, this is lower Q. So what can I conclude from here? High Q, okay, which means that the bandwidth is actually much narrower, okay, or the bandwidth is much more tightened. If you take a look over here, so it's just simply from 5.1 to 3.1. However, for case 2, okay, the bandwidth is actually from 3.1 to 10.6, which is definitely much bigger as compared to case 1. And hence for case 2, you can see that when the bandwidth actually increase, the Q actually reduce. Hence from here, okay, I conclude that bandwidth is indirect proportional to Q. When the bandwidth is high, Q is low. And when the bandwidth is low, Q is high. So this is the conclusion that I draw from this example here. Next, let's take a look on the selectivity factor Q of a bandpass filter. So we have two forms. One, we call it a series resonator. This is what we call a parallel resonator. A resonator is simply the L and C, either they are in series, or L and C, either they are in parallel. And together with the resistor, they actually form the resonator circuit here. Okay, so this is the circuit Q. Okay, how can we compute the circuit Q? Is actually governed by this equation here. This is the series reactance, okay, by either the L or the C, as you can take a look over here. So this is the total series resistor, okay, so which consists of RS plus RL, the total series resistor over here. So from here, I can compute my circuit Q. Let's take a look on the parallel resonator. Okay, please take note over here. For parallel resonator, is actually so-called opposite of a series resonator. For series resonator is actually the series reactor over the total series resistance, as you can see from this point here. But for parallel resonator, it's actually the total parallel resistor over the parallel reactance. So this is the key difference here. Okay, take a close look. This resistor is on top, but for series, the resistor is below. And how can we compute the total parallel resistor? You can see that RS is parallel with RL. So this is what it means over here. And again, for the parallel reactor, okay, we can take either the capacitor or the inductor one. Doesn't matter at all. So next, let's understand, okay, if I want to achieve a high Q, how can I achieve this high Q? Okay, I can do two things. Okay, either I can increase the series reactance or I reduce the total series resistor. Okay, so for parallel circuit, okay, if I want to have a high Q, okay, I can again increase the total parallel resistance or I can reduce the parallel reactance. So with this kind of combination, I can also increase the Q factor. Okay, for example, if I want to reduce my Q factor, okay, so what I need to do is I can reduce my series reactor and also increase my total series resistance. Okay, so vice versa, depend whether you want to have a high Q or low Q, you can change this accordingly. Hence, this is what it means by selector factor Q of M-pass filter. Okay, let's take a look on this diagram in order to fully understand the selectivity factor. Okay, the higher the Q, okay, the sharper the resonator is. Numerically, the Q factor is a relationship between center frequency and the 3 dB bandwidth. Okay, in a LC resonance circuit, it is also the relationship between the LC and R. Okay, let's take a look over here. So from here, you can see that this is high Q, Q of 100. Okay, like what I mentioned to you earlier on, when you have a high Q, the bandwidth actually reduce. Okay, they have a indirect proportional relationship, bandwidth versus the Q factor. Okay, when Q actually reduce, you can see that the bandwidth start to increase. And when it further reduce, you can further see that the bandwidth actually further increase. So this is a diagram illustrate on this Q versus the bandwidth. Okay, so this is what I want to describe. Q factor is the relationship between center frequency and the 3 dB bandwidth. So this is the center frequency, is actually a relationship between the 3 dB bandwidth. Okay, with this, I'd like to end my discussion. Please help to like and subscribe. Thank you so much.